Okay, you have an exam for me, right? That should be in order, neat, stapled, right? And ready to turn in. So go ahead. You can kind of pass it. Huh?
Do you need this on the front?
I don't need the test unless you have work on the test that I need to see. And then in that case, you should have put it all together for me. What I don't want to be doing is, going back and forth, going, okay, here's their work, and then I have to go match it up with your picture, and then this is the first exam, so I'll be lenient on this first one, all right? But the idea is to turn in some work that you can be proud of. Across the hallway in the tutoring lab. Paperclip's fine. Anybody else? Are these okay? So, anyone else?
Yeah, that's what I.
You have a question? What you got?
His brother's super simple.
If we use the exams to get pictures, we want our work to go through for the next week.
How do you mean? Like
for two, I use that Pentagons for my colleagues to do my work to go through that page.
yeah, so like in the future, if you're going to do the problem with the Pentagon, right? And you have a bunch of work on the picture that I provided you, and then you have a separate page with separate work, then at least, tear the two apart or make a copy or do something, that way, I'm looking at number one, here's all the work, and here's number one. All right, you have these for what? You had this one for 2 weeks, so my intention was that you kind of put it all together, knocked them out one at a time over the 2-week period, and part of this is I'm trying to see where you all are in terms of presenting your ideas to somebody, because I think that's an important skill that I talked about, I think, in the very beginning. You're going to be working normally with a group of people in a real job. Are you going to be able to present your ideas to them in a clear manner? Or is it just going to be a bunch of crazy ideas all over the place that you can't explain to anyone and no one can follow you? So that's what I'm looking for. Your mathematical penmanship and clarity. So we'll see. I mean, it's something that you'll work on. I remember distinctly a student I had for Cal 3 semesters, a couple of semesters ago, and he was an outstanding math student. He knew what he was doing, but his writing was horrible. And so we slowly worked on it in one exam at a time. By the end, it was like night and day. And he understood what it was like at the end to write down his ideas. And I think that benefited him, and I'm hoping that'll benefit you. Anyone else? Last call? Just get your name on it? Okay. As you're handing those in, I shall hand you your next one. You know what? Hand this group back right there. Need one more?
You don't need to take one.
This one's due in a week. And the reason why is because everything on this exam can be done as of the end of today. So there's nothing that you have to wait for on this one. And I think this one's a little more straightforward. This one, the problems are a little bit more like the problems out of the textbook. A little bit. But let's talk about the first one before we start looking at this second one. I hope that after you had the opportunity to look at the first one, you were made aware of the fact that you can't wait till the last day to try and do these. I guess you can, But if you do, there's potential to run into some hang-ups. And if you just look at them initially and go, oh, yeah, no, I get that, I'll look at that in a couple of days, you could find yourself in a situation where you really don't know what you're doing, and you're stuck and you've got 24 hours to get it done. And that's not the intention of a take-home exam. The intention of a take-home exam is for you to chip away at it one at a time. Take one or two, one a day, right? If you do one of these a day, you're good to go. This next exam's only 5 problems, so you have 7 days, 5 problems, just 1 problem a day. And I want you to reach out to me. I had a lot of people reach out for help, taking pictures of their work on their cell phone and texting it to me. I have no problem helping you like that. In fact, that's what I want. I want a dialogue back and forth. I want to know what you're thinking. I want to know how you're approaching the problem, but I can't do that the day before the exams due. Like yesterday, I can't even tell you, I must have received at least 40 or 50 text messages yesterday alone from students in this class, which I invite that, but just not the day before the exam. Because when you send me something and it's so far off from where you're supposed to be, it's like, wow, I have to get you, a pretty far distance in a very short period of time. I'm just going to tell you how to do the problem. I want you to think through it. I want you to kind of stumble upon it yourself. So that makes sense? Okay, let's look at this second exam. Read the first question. Find the equation of the plane. Right there, right off the bat. What do you need for the equation of plane? That's what you should be thinking. What do I need to define a plane in this class, right? Normally it's what? A point and a normal vector. That's it. So the question is, can you resolve a point and a normal vector for the plane that you're looking for from the given information here? And then the second problem, find the equation of a line. Okay, so now you have something different. For a line, you need what? Point and a direction vector, or 2 points, right? Okay. 3, find the shortest distance. Okay, well, we talked about that in class. There were 2 different formulas that we worked with when it talked about distances. So which of those 2 does it fall into? Well, you'll figure that out, right? Number 4, we haven't talked about 4. Given a vector function, how do we take the limit of a vector function? Now I'll give you a big hint on number 4. Number 4, your ability to do number 4 is going to really fall back on how comfortable you are with taking limits. Specifically, L'Hopital's rule and certain tricks that you use sometimes when you see certain forms of, like infinity over infinity, things like that. So if you have some holes that you need to fill in, that's where you need to go back and look at L'Hopital's rule. All right, number 5, that's a very interesting problem. I have a picture I can show you for that one, but I'm going to do problems somewhat like that today. Now all of these say, like on number 1, it says, see at the end it says i.e., find the equation of the green plane below, and there's no picture to go with that. That's because I have this document in a CDF file, which I told you all about at the very beginning. I have that file available so that you can open it up and you can rotate things and look at the pictures that go with this stuff. I will put that out on our website today in Canvas. You can download it. If you went and did the CDF player, then you can open it and take a look. If not, then you can ignore all those little things at the end. Understand? Okay, let's talk about the first mini exam. I just want to breeze through it. I definitely don't want to go through how to do each problem. We don't have enough time for that. That way you'll know right now. Okay, so on the first problem, u dot v, second one. Thank you. On the first one, you had the plane and stuff, and the person, and then wind. So basically, that creates 3 vectors. You have a vector that represents the plane. You have a vector that represents the wind, which was blowing west. And you have a vector that represented the person that was walking backwards in the plane. So you have 3 vectors, and you just go tip to tail, tip to tail, tip to tail, all 3 of them, and you get a resultant vector. That resultant vector is the direction, will give you, well, from the resultant vector you can determine its direction, and then you can determine its length, which would give you the speed. That's the way that one was done. So how you get these three vectors is all in the words here, right? 400 miles per hour would have represented the length of this vector. Southeast would have represented 45 degrees this way, which would have meant the actual angle for the vector would have been, what? 315, right? So, and you just resolve each of the components for each of these vectors and then add them up. All right, so number two, you can make this problem really, really hard, or you can make it really, really easy. It just depends. Sometimes you make it easy and you aren't supposed to make it easy. You're making it too easy. First thing you had to do is know what the angle is for all of these. I think that's probably the easiest way to start. And so maybe you needed to Google that. But what's the angle, what's the common angle in a regular pentagon? 108? So you know that all those angles are 108 degrees. You already know that the length of U is 1. You already know that the length of V is 1. You don't know the length of W, though. Not right off the bat, because W obviously is not the same length, right? But you could easily get the length of W if you just use the fact right here, create this triangle here. This has a length of 1. This has a length of 1. You're trying to find the length of W, and so you have a triangle that looks like this. This 1, 1, W magnitude, and then you know this is 108, which means these two angles have to be the same, right? So you can figure out what those are. What was it? 36. Once you know that, you're in business. You can start breaking each of these vectors down. You have to figure out like what direction is U pointed in. You know, what's that direction? U and V are pointed in opposite directions, so the angle between them is 180 degrees. Yeah, so that's, I don't know if that's, did anyone have any questions on that? I'm not going to get into specifics, but, no? Okay, oh, number 3. Okay, so number 3, what you should have had on number 3 is, you're trying to figure out what B value makes these orthogonal, right? So you just dot product those two and set it equal to 0. And when you dot product those two vectors together, you get b to the 4th plus, I don't even remember, equals 0. Some 4th degree polynomial in B. And the question was, how do you solve a 4th degree polynomial in B? And I did not want you using solve something like this. Does anyone remember what the last number was? 120? Okay, so to solve this, you go back to college algebra and something called the rational zero test. And if you didn't do that, if you did like a guess and check method or something, you should go back and look at this rational zero test. And so what you do is you take all the numbers, or you take the number in front of the highest power of b here, 1, take the number constant by itself, you write down all their factors. And you make this list. Does that sound familiar? And then you do this synthetic division with each of those numbers in the using the coefficients of here. A 0. And every time you get a 0, you know that this right here is a solution. And you should be able to do that 4 times, and you should get 4 different solutions. And that's the way it's done. That's the way you solve a 4th degree polynomial equation if you have no technology, all right? And it's not guaranteed. This will only find rational zeros. This will only find answers, these will only find answers if they are fractions. So like 4, that would work. 4 is a fraction, right? 1/2, this test would find it. But if we had a solution in here where maybe b was like the square root of 2, this method wouldn't work. But I didn't give you a problem that did that intentionally. Understand? Okay. I didn't want you to do guess and check. If you did, I'm not going to take off full points, but that's one of those problems where if you're hung up on it, you're like, well, I guess he wants me to just guess on the answers, then that's where you would have reached out to me and said, hey, you know, I'm on this problem. I'm getting some answers by guessing, but is that what you want me to do? And then, you know, we open up that dialogue and I tell you, no, that's not what I want you to do. What I want you to do is find it a different way, all right? That makes sense? Okay. So if ever in doubt while doing this exam, if ever in doubt, just reach out. All right, this one, is this worth going through? The length of the diagonal is from here to here. Did I send this out in a CDF?
Yes.
I did, right? So if you have downloaded the CDF player, you could have rotated that around and taken a look at it if you had any question as to where things were. So you're going from this point to this point. That's the diagonal. So two of those points, I'm not sure which ones they are. You just connect them with you make a vector between them, you find its length, right? That's the answer to the first part. The angle between the vectors shown. So you have to create this vector and then find the angle. So you use the, what? Theta is arc cosine. Then dot the two vectors, divide by the magnitude of the two vectors, and you're done there. And then see the volume. So how do you find the volume of this? You have to do that triple product, and you need three vectors. And it can't just be any three vectors, or it can be. It's not supposed to be. It's supposed to be, let's see, you take like this vector's okay, right? And then you take like this vector up here. If you take those three and do a triple product, then you'll get the volume of the solid. Okay, that's that. And then the last one. Okay, so a lot of people made this one harder than it had to be also. This is a tetrahedron. It's basically, it's lying in the first octant. And if you look at like this back triangle right here, and you just take it out and put it on a flat sheet of paper, this is a right angle right there. So you have something like this. You know that this is 2 and this is 2. And since you know that, you can just go area is 1/2 base times height, because you have the base and height. So that's what? Half of 2. So this is just 2, right? That's just 2. But how many of these do you have? You have this one, and then the bottom, right? This bottom one. So you have 3 of those, right? So far your area is 6. And now what you need is this front face that covers it up, if that makes sense. And for that one, I did not want you trying to find 1/2 base times height. If you did that, I'm not going to, again, penalize you, but I wanted you to use something in this class. So if you just create a vector that goes from here to here, and a vector that goes from here to here, which you can do because you have the points, right? Then you know that you have a formula that allows you to find the area of the parallelogram spanned by those two vectors. And so the triangle is half of that. So all you'd have to do, if we call this vector A and we call this vector B, you just find half of the magnitude of A cross B. And that would be your other area. Anyone remember what that turned out to be for that front? This was 2 root 3? Yeah. And then, everything together? Oh. Okay, so then you do this, and then plus 2 root 3 together. That's your total surface area. That would be it. Okay. So that only took me like 5 minutes. No. That one wasn't, there was a lot of little details in there, right? You have to pay attention to? Pardon? There's another one? Oh. Oh, okay. So this one, yeah, I kind of gave you a hint. Let's see. Find the center of the sphere, right? How did you get the center of the sphere? Go grab one. Yeah, you have to write it in its standard form, which means you had to complete the square on it. So the first thing you do is you complete the square on this equation, and you get it to look like this. HK, sorry, L. Right, you make it look like this, and then you know what its center is, right? Its center is HKL. So you know this point. Find the vector equation line passing through that point and the point of intersection of this line with this plane. So how do you find a point that lies on this line and this plane? Yeah, you just come into this equation, you replace this x with what? T from here. And then you replace this y with negative t plus 1. You replace this z with this. And then you'll have a single equation in t. You solve for t. Once you know what t is, you plug t back into this, and that will give you a point that lives on that line that coincides with a point on this plane. So you'll have that second point. And once you have 2 points, you can always find the vector equation of the line pretty easily. Right? That's it. Okay. So please just keep in mind, I mean, the moral of the story, if you can take anything away from this first exam, is if you can do all this and you don't need my help, more power to you. Okay? Good. You're in a good place. But these exams are intended for you to need help. I mean, I'm asking you to reach here. And I'm willing to help you along, all right? So don't be afraid. I know normally that's not the case with tests. You know, you're not supposed to ask anyone. You know, you don't want to feel like, I guess you feel like the instructor doesn't want to be bothered by it, but I actually want you to bother me with it because I want to know how you think. I just want to know how you approach things, all right? All right, let's get on with today's material. I've fallen a little behind on the homework solutions. I only have up through 10.7 done. I started to do 10.8 on Friday. I had this huge headache. I started doing the videos, and I did this problem, and I messed up on it, and I was all frustrated, and I just walked out of the room. And I'm not going to post that video, and so I'm behind a little bit. So I'm going to try and do some more solutions and get 10.8 up. Maybe later today, I don't know. Depends on how my day goes. All right, so 10.7, vector functions and space curves. Were there any questions before I move on? No? Okay. All right, so we have actually studied, this section is just about vector functions. We've already studied a vector function, believe it or not. The vector equation of a line we said was r of t was equal to r naught plus tv, right? And then when we put things together, we got this thing that looks like this, right? And it would have 3 pieces to it if it was in 3-dimensional space, or if it was in 2-dimensional, it would only have 2 components. And the stuff in here would be like numbers, and it would also possibly have t in here, wouldn't it? So it'd be a mixture. Maybe it'd look like this: 2 plus t, and then maybe this one would be like 3 minus 2t, and maybe this one would be 4t. Who knows? Maybe that's what it would be, right? This is an example of what we call a vector function. The thing that makes this a line, though, what I'll point out, is that each of the component functions is linear. Do you see that? And because of that, this particular vector function draws a line. But if we now take away the restrictions and say, you know what, forget this whole TV thing, and I just tell you, hey, look, I'm going to create a vector function. It's going to have either 2 or 3 pieces to it. And in here, I'm just going to put any function of t. No longer linear. Could be quadratic, could be square root, could be sine, doesn't matter. Then what we get is a broader category of functions that includes lines, but includes a lot more. And these are called vector functions. And so if you have a function, r of t, which is 2-dimensional, which is f of t and g of t, or 3-dimensional, f, g, and h of t, where t is a real number, f, g, and h are real valued functions, then it's called a vector function or a vector valued function. Three is this class includes topics in vector calculus. Have you heard that before, vector calculus? This is why, because now what we're doing is we're defining a class of functions that are called vector functions. And so our functions take in a number, right? They take in a value. That's what I just said. The domain is the reals, and the range is vectors. So let me show you a little y was the output. So back even in college algebra, we had talked about this idea, and we had this idea of a domain and range, right, where f did this. F took something, spit something out. And back in Cal 1 and Cal 2, the X that we plugged in was usually a number. Not a hashtag, that's number, okay? Spits it out, right? A number, right? Number to number, right? Number in, number out. That's Cal 1 and Cal 2. We would look at this right here, this function, the way we write it as we advance and get higher in mathematics, we would say that F here is a function that goes from R into R. Because it takes a number, which is off the real number line, right? It takes a real number, and it spits out a real number, doesn't it? That's what we've been studying. What we're introducing now is this concept of we now have a function that takes in a number still, okay? We call it t. We like to call it t. This function, we don't call it f, we call it r. And what it does is it spits out what? Vectors, right? Vectors. So I'm just going to put v for vector, okay? Spits out vectors. Could be two-dimensional or three-dimensional. Got it? So this function, if we were trying to look at this, this would be like the r function is going from r into what? So if you take a number in and it spits out a vector, that vector is either going to live in like two-dimensional space or three-dimensional space, right, in this class? So this is either going to go from R into R2, or it could possibly go into R3, depending on if the output's two or three-dimensional. Do y'all follow? That's all we're studying in this class, pretty much, are functions that are doing this. But there's no restriction in mathematics that stops us here. You can have a function that goes from any space to any space. So in general, there's no restriction on it at all. I can define a function right now if I wanted to. I could call it f, and it could go from R4 into R7 if I so desired. It would take in 4 different values and spit out 7 values. What we're interested in now is a vector function which takes in real numbers as the domain, and the range is vectors in R2 or R3. All right, so some language here. When we're given a vector function, these little kind of mini functions that live inside the vector function, these are called our component functions. So you might have 2 component functions, you might have 3. But because I'm calling this one f and this one g, that means they don't have to be the same function, right? This could be some function of t, could be completely unrelated to that first component. So component functions. All right, very important. The graph of a vector function in R2 or R3 is a curve. All right, now we know that there is a specific vector function that is a straight line, right? We said the line function is a vector function. And I think we might argue whether or not right now a straight line is a curve. Should we argue about that? Or do y'all think a straight line in 2 or 3 dimensional space is a curve? Yeah, I mean, how are we going to define curve, right? So look, for us, we're going to say straight line is a curve. Now, it has no curve to it, but it is a curve as opposed to it is not a surface, okay? If I graph this, I'm not going to draw a surface. I'm not going to draw a solid block or blob of something. I'm going to draw a curve that lives in either 2 or 3 dimensional space. Very important for us to understand this because later on we actually do want to draw surfaces. And what we'll realize is we can't use this. This isn't enough. So we need to add something to it. So here's an example of a vector function. I'm going to have to make this a little smaller. This is the vector function r of t equals t squared 1 minus t cubed. And I believe that's written down there also. So we could make almost like a t-table for this. I don't know if y'all can see this on the bottom. Do y'all see R of t down here? Okay, so t comes in, a vector comes out, right? The vector is t squared 1 minus t cubed. If I plug in 0 for t, of course, I'll get what? The vector 0, 1, right? So it's almost like I start a watch. Okay, at t is 0, at the very beginning, I draw the vector 0, 1, which is this red vector right here, right? Don't go left or right, go up. This is two-dimensional, so I'm on a flat sheet of paper. Yes? So this point at the end of the vector corresponds to the first point on the curve. Now I let t go to, let's say, 1. So if I plug in 1, what do I get? 1 here and then 0. So now I should be here, right? So let me advance the time for us. Oops. Let me turn my phone off, sorry. Let me advance. Notice I'm going to advance this and just, this is the values of t right here. So let me advance it and just watch the red. You see it? And when I get to 1, that's where I am, right? All the other points in between, right, between t equals 0 and 1 were all of these. And then if I keep doing this, of course, I'm going to just draw the rest of this, right? Pointing to, right, that point is what corresponds to the curve. We good? So let's take a look at a three-dimensional vector function. And this is a critically important example because there's something happening in here that we're going to see for the rest of this class. And that's the whole cosine t, sine t. So I'll ask you to recall, remember back from pre-cal, that if you have the unit circle, right, the unit circle, that if I take a point out here, and this length is 1, and this angle is theta, right? Which I'm not going to label theta. I think I'm going to label it t instead of theta. Then the coordinates of this point are given by what? Cosine t, sine t. So if I start letting t start at 0, and then let t start going and getting bigger, it's going to draw this unit circle, isn't it? Yes? Y'all remember that pre-cal? Okay. If I change this 1 to an r instead, how does this formula change? R in front of cosine, r in front of sine. That look familiar? All right, so when we come back and we look at this right here, we have how many component functions? 3 component functions. Look at the x component and look at the, I'm just making sure my camera's recording. Okay. The x component and the y component. If I ignore the z component completely, the x and y component would just draw me a unit circle, wouldn't it? If t starts going, if t is bigger than or equal to 0, I'm just going to start drawing a unit circle. But see, I'm in 3-dimensional space, so the question is what's happening to the z coordinate? Well, look at the z coordinate of the point. That's controlled by this component function, which I don't know if you can read that. It's t over 5, which is the same as 1/5 t, right? So what's happening? What is happening with z as time gets bigger? It's going to get bigger too, right? Now it's scaled by 1/5, so when I plug in 5, I get 1, and when I plug in 10, I get 2. But it is growing, isn't it? It's growing linearly. So do you see what this is going to draw? Can't draw a sphere. Why can't it draw a sphere? Sphere would be a surface, wouldn't it? A cylinder? A cylinder would be a surface also. A spiral? Helix, something like that. So imagine what's happening is you're trying to draw in 3-dimensional space. In the xy plane, which is this, you're trying to draw a circle, right? You keep on trying to draw this circle over and over and over and over and over and over. But as you're doing it, your z coordinate must grow. So it's going to be something like this, shouldn't it? There it is. I'm just going to press play and it's going to start drawing this for us. And let me pause this and let me kind of look at it from the side. Can you all see that? You'll see how that looks. If I look at it from the top though, what? It looks like a circle. Now, because of perspective and the way this is, when you look from the top, if we were truly looking from the top, you would have to go way out to infinity though. You would actually just see a single circle, right, if you look straight down on it. Understand? So it's the z that's growing that creates that spiral. Now, let me get in here. Let me see if I can mess with the code. Sometimes I like to mess with the code in the middle of class just for fun. Shit, come on. Let me do this. I'm going to copy that. I'm going to draw another one right next to it. I don't know how this is going to turn out, but I'm going to change the t over 5 just to t. Shit, what happened? Where is it? Where is it? There we go. Whoa, what the hell? Hold on, let me go back up here. Oh, I forgot a comma in here. That's what it is. Syntax error there. There we go. Okay, so there. Now you can see them both, kind of. Y'all see them both? So which one is the one that's t over 5 and which one is the one that's just t? So t over 5 is which one? Smaller one? And t is the bigger one because it's growing faster. Make sense? And if I change that to t over, what, 10? Let's go t over 4 so they'll be close to each other. Right, so it's hard to see it that way, but I think you get the idea, right? You get the idea?
If you did negative cosine and negative sine, could you make the opposite to make it a double helix?
You mean which way? Oh, I'm not sure what you mean. Like to draw it side by side to create a double helix?
Right, if you did negative cosine, negative sine, would it go the other way and then wrap around each other? Make a double helix?
Oh, okay, I see what you're saying. That's an interesting question. Let's try this. You want me to go negative cosine, negative sine, and t over 5? Let's see what happens. I'm not quite sure that's what you wanted. Why don't we do this instead? Why don't we go sine and cosine here? Whoa, what the hell? There we go. Look from here. It's kinda, I don't know if that's what you wanted either. But you can start messing with this. I mean, you get the idea here. I hope you get the idea. What else? I want to do something else. Hold on. Why don't I do this? Cosine. What would happen? What do you think would happen? Right now they're the same. I don't know if y'all can see that in my code. That's the same as this, right? What would happen if I made this 2t, 2t? What would happen? What happens when you put a 2 in front of a sine function or a cosine function? What happens to its period? The period's going to get shorter, 2 cycles in a normal cycle. So that means that it's probably going to draw that same spiral, but it's going to draw 2 of them in the same amount of space that the other one draws 1. So it should be a more compressed spring. Let's see. We'll look at it from the side. It's really hard to tell. I need different colors on these. Okay, you get the idea.
For his idea, couldn't you do 1 over sine or 1 over cosine?
So it would be more like a helix.
I don't know. We could go crazy with this. We could just start having fun. So look, you know what? Get on Wolfram Alpha, and go type in. I think they'd want you to use a brace. Try it. I don't know if Wolfram Alpha will do this or not. You know, use a brace and then type in your 3 functions and put plot or put in front here something like parametric plot, and then see what happens. And I bet you can mess with it yourself. How about this? What if I change, let me change that one back to the other one. What if instead of putting cosine t, I put 0.5 cosine t and 0.5 cosine t on the second one? It's going to be thinner, closer, so a tighter spring. Remember, on the unit circle, what was that number in front? It was r cosine theta, r sine theta. So if I make the r 0.5, shouldn't that change the radius? There we go. So, do you see it? Can you all see from the side? Like this one has a radius of 1. This one has a radius of 0.5. Understand? As you can imagine, you can go crazy with this shit, right? I mean, you can draw pretty much anything you want in 3-dimensional space with a vector function. And that's pretty cool because when you go back and you look at Cal 1 and the problems that you ran into in Cal 1 and Cal 2, a lot of the things that we needed to do all of our calculus was that we needed this to be what? F was some function of x, didn't we? We always needed to be drawing a function where it passed the vertical line test, right? And in Cal 2, you ran into problems like if you were trying to find the area under this, right? Then you would just use your integral formula. But if your function, if your curve looked like this instead, wouldn't you have to look at it the other way and change your integration variable and stuff? See, right? And then you'd have y bounds on your integral, and you would integrate with respect to y. What we're getting at here, okay, believe it or not, is that it may not matter anymore. If you can draw the curve and t is some variable that's not on your graph, then you're no longer required to have the condition anymore, vertical line test. It all goes away. And you can draw things that, you know, crosses through itself and does all sorts of crazy stuff, and you're not stuck here anymore. And it's a brilliant workaround, I guess. All right, let's continue. All right, so just like we did in Cal 1, right, you got into Cal 1, they're like, welcome to Calculus 1. We're going to study something called limits, right? And we're going to look at functions. We're going to look at their limits. And then you suffered through limits for a while, didn't you? All right, now we have the same thing with vector functions. We need to define what a limit is with a vector function. And it turns out that it's actually a really nice thing, okay? There's no new craziness to it. If you're given a vector function in 2 or 3-dimensional space, the limit of the vector function is simply the limit of the component functions. That's all it is. So if I want to know the limit as t approaches a of the vector function r of t, I just take the limit of each of the component functions individually. So that right there is one of your problems on your take-home test, right? That's number 4. You just need to find the limit as t goes to infinity on 3 separate component functions. Once you figure out what those 3 limits are, you get your answer. Notice, though, that your answer is a vector. Your answer will be a vector. So, you know, whatever this limit goes to, let's say that goes to 2, and this goes to 5, and this goes to -1, then your answer will be that vector. So here's an example. Can everyone read that okay? Find the limit as t goes to 0 of r of t. So the limit as t goes to 0 of the vector function cosine t sine t over t e to the t minus 1 over t. So this just equals the limit as t goes to 0 of cosine t, the limit as t goes to 0 of sine t over t, and the limit as t goes to 0 of e to the t minus 1 over t. All right, go ahead. I'm going to give you a minute to get each of those. What? Okay. Go ahead and try and get those limits on your own. If you did not turn in a mini exam today, if for some reason you did not, I would like to talk to you after class. I don't know if anyone did, but if you didn't, please speak with me after class. Does anyone have an answer yet? You got one? Okay, I'll ask you for the answer if you want to share it in just a second, okay? Yeah? All right, you ready? Do you want to volunteer your answer?
Sure.
Go ahead.
I got 1, infinity, and negative.
Right here?
Yeah.
Any others?
Good.
I got 1, 1, and 0.
1, 1, 0.
I got 0, 1, something.
Okay. 0, 1, something. Okay. I've never had that come out, but I get.
Something I mean that I couldn't find.
I got you. I got you. Someone say something else?
Infinity 1
Infinity, 1, infinity.
and beyond.
Yes? Anyone else? Okay, let's talk about this. No? You want to volunteer? No? Okay. What happens to the cosine function as t goes to 0? Cosine of 0 is just 1, right? So you just get 1 for the first one.
Oh, yeah.
Okay, 1, 1 something. Hold on, 1, 1 something. All right. Sine t over t. Okay, so what sine of 0, right, is 0 over 0. 0 over 0 is an indeterminate form. You don't know what that is. So you have a couple of options. You either remember a formula that was given to you at the very beginning of Cal 1 that they said memorize this, and they told you that this was 1, or you use L'Hopital's rule. L'Hopital's rule, show of hands, L'Hopital's rule? Okay, so how about hands down? Have no idea or I don't remember at all L'Hopital's rule. Okay, you're going to have to get tightened up on that, okay? So who's comfortable with L'Hopital? Explain it. Explain it. You want to explain it? How do you do L'Hopital's rule? When is the only time you can use it?
When you have 0 over 0 or infinity over infinity.
Okay, this is the only time you can ever use L'Hopital's rule, right here. And it doesn't matter. You can have plus or minus infinity. It doesn't matter here. Okay? Anytime you see this form in a limit, then who else is comfortable with it? Do you want to tell me what you do if you have this or this?
Just the derivative of the top and the derivative of the bottom.
Okay, so you just take derivative of the top and the bottom separately, right? Not the quotient rule.
Right.
Okay, so all you have to do in this problem is do a new limit as t goes to 0. Take the derivative of the top, which is cosine t. Derivative of the bottom, which is 1. And now do it again. So not do the derivative again. Try the limit again. T goes to 0. Cosine of 0 is 1. 1 over 1 is 1. So you get 1. So far, let's see. This one's out, and this one's out. Okay, so it's these might still be the same because something that was kind of vague. Something could be 0. All right. So t goes to 0. What's e to the 0? 1, 1 minus 1, 0. So the top's headed towards 0. The bottom is headed towards 0 again. L'Hopital's rule. Take the derivative of the top. What's the derivative of the top? E to the t. What's the derivative of the bottom? 1. Okay, what's e to the 0 now? 1, 1 over 1? 1. Ooh. So the something wins. The something wins, and that something was 1. You just didn't feel like telling us, did you? Right? So it's the vector 1, 1, 1. Okay. Now, for those of you who have experienced a lot of the L'Hopital's rule, is this what we just did? Is that a good treatment of L'Hopital? Like, is this L'Hopital in a nutshell, or does it get a little harder? It gets a whole hell of a lot harder than this, because there are other forms that aren't as easy to work with, especially when you get something like this. When you have a limit and the base maybe is going to infinity and the top is going to 0, that's the trouble. And there's a certain way we attack that. You cannot just go to this. You have to make that look like this first. And there's a lot here. That's exactly what your test is going to ask you to do. It's going to test you on whether or not you remember these concepts from Cal 1. All right, and if you don't, you know, you've got some time. Come ask me. I can even point you to some of my own videos from Cal 1 classes that I've taught where it's an entire day's lecture or 2 days of lecture with me going through L'Hopital's rule. So just let me know if you're having trouble with it. That was fun. It's on my YouTube channel. If you try and find something on your own, I think that the topics are listed by, you know, like day 14, it'll say L'Hopital's rule. But try and find like a more recent semester. All right. Continuity. So just like in Cal 1, we talk about limit of a function. After the limit definition, then we talk about continuity. And continuity back in Cal 1 roughly meant that you could draw the function without picking up your pencil. That's basically what it meant. That there were no jumps or breaks in the graph. And that's pretty much what it's going to mean here, is that you can draw this curve in 2 or 3-dimensional space without having to lift up your pencil or marker, whatever it is you're drawing with. All right? But there is a precise definition, and the definition says that in order for a vector function to be continuous at A, we need this limit, or this equation to be true. So remember from Cal 1 that if you had a function that if you approach it from the left and from the right, and they're headed to the same place, then we say the limit exists. If that was an open circle like this, let's just say that this is L. Right here in Cal 1, we would say that this function is, the limit exists at A. And the limit would be L, because from the left and from the right, they're both approaching L. To make it continuous, we have to fill that dot in. Same exact thing here. This is the filled in dot. This is the limit coming in from both sides. I don't want to go back and do a full treatment on continuity again. But I'm pointing out that this is the same definition from Cal 1, just with vector functions instead. All right, let's describe this curve. I just want you to look at it and tell me what it draws. Like, is it your spring, you know, that we had earlier? I mean, what is that? It's a line, right? Linear, 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 right? In fact, if I broke it apart, couldn't I write it like this? And this would be my R naught, and this would be my direction vector V. So that is a line, right, in 3-dimensional space. So we just need to be able to identify. When we see it, we're like, oh yeah, sure, that's a line. All right. right, find the vector function for the line segment. I have no idea why this is here. We already did line segments. But let's practice because we haven't done it in a while. How do you find a vector function from one point to another? Pardon me? We are going to restrict t. What are we going to restrict t between? 0 and 1, good. All right, and let me define my r of t. It's going to be a line, right? So I need an r naught plus tv. What's r naught going to be? The first point converted to a vector. So 3, 5, 9. Good, Karen. I'm glad to hear this. Plus t times v, and v is going to be? So you're going to take this one away from this? Or take that one and subtract those. So -5 take away 3 is -8. And then 7 take away 5 is 2. And then -3 take away 9 is, was that -12? And our restriction, I'm going to write t between 0 and 1 a little different, just so we see two different notations. T is an element of the interval 0, 1. And we can put that together, right? I won't do it. That's your line segment right there. But it's a vector function. Ooh. Whoa, okay. So all of a sudden we go from that to this. This is a cool problem. Everyone take a look at it, read it. I'm going to show you the picture first. Find the vector function and its domain representing the intersection of these cylinders. So from last class, do you remember us talking about the quadratic surfaces? And if we saw something like this, x squared and y squared, and there's no z in here, right? That would fall into one of our categories. And that is actually a cylinder that opens in which direction? Or that, we have a beer can, an infinite beer can, right? That goes up the z-axis and down the z-axis, right? And then this one, again, has two of our variables squared. The x variable is missing. So that's another cylinder, but that one's going the x-axis, right? And these two cylinders come together at the origin, and they intersect each other. So here's our picture. Yeah, I like it. Which one's smaller? So the green one is smaller. I should probably rotate this around. There we go. So that way it looks like right-hand rule. So the x-axis is coming out towards you, right? X-axis coming out towards you there. Stay. There we go. All right, so we have a cylinder. I want you to draw me the intersection of these. That's what I want you to do. I want you to come up with a vector function that would be 2 or 3 components. We're in 3-dimensional space, right? So it's going to be 3 components. My question to you is, what are these 3 component functions? And not only that, what's the restriction on t that, I gave it away down there. What's the restriction on t that will draw the intersection? That's pretty cool, right? I mean, if we can do that, that's pretty awesome. That we'll be able to draw this. We will actually be able to take their intersection. Can you see them? I just brought their intersection in there. Let me take the cylinders out of here completely. That's what I'm talking about. That's the intersection, right, of those 2 cylinders. I want you to start drawing me both of those curves. Draw those curves with the vector function. So, that's what a vector function does. It draws a curve. So I want you to come up with the vector functions. And there's going to be 2 of them, right? Why is there going to be 2? We have 2 different curves, don't we? So we should have 2 different vector functions. So what is it? What are the 2 vector functions that draw those 2 curves? And you might have a natural question for me like, why? Why in the world would I even care to do that, right? Well, let's say that you own the company that creates these pipe fittings for major cities for their underwater or underground, whatever it is, sewer systems. Maybe it's made out of copper. And you have to weld these things together. You're trying to get some sort of cost analysis, right? You need to know how much weld this is, right? How much weld is that? Well, guess what we're going to be able to do in a little while, a couple of sections from here. If we have a curve living in three-dimensional space, we're actually going to be able to find the arc length of it. We're going to be able to find the length of the curve. So then you'd be able to find how long this is if you took it off the paper and stretched it out, and then you would know how long that bead of weld would have to be, and that's part of your cost. You're going to have to pay someone to do that, right? Materials, labor. And then you can just look at it like, because we can do it. I mean, that's just cool. We can do it. Who cares? We can do it. It's not some mystical thing we can't touch. Right? We can get it. All right, so where are we going to begin with this? All right, where are we going to begin? We don't need the pictures. Tell me about a point that lives on the intersection. Some point that lives on the intersection. I'm just going to call it X naught, Y naught, Z naught. Tell me about that point. Tell me about it.
On the first one, Z is free. Yes,
Are you talking about this one?
Yep.
Yeah. So this point, if this lives on the intersection of both of those cylinders, this point must satisfy that equation, shouldn't it? And it must satisfy this equation simultaneously. Right? That's what we have to have happen? Okay, so let's talk about how are we going to do this. I said we wouldn't need the picture again, but I'm trying to give you a hint here without giving this away. If I turn this and I look at it down the x-axis, okay, which is way out there towards you, right? If I go way out there and you're looking at it, what is that? It's a circle, isn't it? What radius is that? It's the smaller circle, isn't it? So it's a radius of 2. Can you draw me just a circle of radius 2? Can you do that? What would you use to draw that in a vector function? What would you use to draw me a circle of radius 2? 2 cosine t, 2 sine t, right? My question, though, is what plane are we looking at here? Like, what are the two variables here? This way and this way. That's y and z. So you want to draw a circle in the yz plane of radius 2, which means that if I go back here, which of these circles right here had the smaller radius? This one right here?
Yeah.
Okay, let's draw that. Let's draw that. That alone right there would draw me a circle in the YZ plane, like this, radius 2. Do you agree with that? In the YZ plane, that would draw me a circle. But I don't want my x-coordinate to just be sitting there doing nothing, right? I'll go back to my picture again. See, this was us looking straight on like this on the YZ plane. If I turn it sideways, look at my x-coordinate. My x-coordinate actually changes, doesn't it? Like the x-coordinate, like it's over here, but then it changes, comes this way, and then it goes back, doesn't it? That fluctuation back and forth is what I need to account for. Y'all with me or not? But keeping in mind that I must be on both surfaces at the same time, I must be able to satisfy this equation. And what is it about this equation that you know has to be true? Come back over here. The y must be what? 2 cosine t, right? This is your y, this is your z. Your y must be 2 cosine t? Yes? So if I go back up to this equation right here, and I rewrite it, and I write x squared plus y squared equals 9, if I solve this for x, do you agree I would get that? And you just told me that y had to be what? 2 cosine t, then I could say that the x would have to be plus or minus square root of 9 minus 4 cosine squared t. Do you agree? And that's what this x component needs to be. If the x component is this, then I will live on this cylinder while at the same time living on this cylinder. Do y'all see these two things coming together? These two by themselves make you live on the smaller cylinder, for sure. But the x coordinate or component function being this means you live on the other cylinder. And the only way you can live on both at the same time is if you're their intersection. So let me just rewrite this bigger. So r of t must be equal to plus or minus. That's why we get two functions. I told you we get two functions, right? And then what? 2 cosine t, 2 sine t. We good? We good? Yeah, we're going to talk about domain restriction, but I don't remember that being what I had down here. I think I typed this in wrong. Let's see, hold on. No, I did it a different way. No, it's okay. It'll draw the same thing. What I did, I approached it a little different than I did that one. What I did is I said, well, you have to live on this first. So how would you live on this? Well, to live on that, you have to be 3 cosine t, 3 sine t. And then I said, but then your z has to follow this, and then do the same thing the other way, and I got a different equation. But it should draw the same curves. All right. So what about domain restriction? Do we have any domain restriction here? Do we have some issues?
If 4 cosine squared t is bigger than 9.
Yeah, could that happen? What about domain? Nothing's going to cause this to go crazy, right? Nothing's going to cause that to go crazy? The only thing that could ever happen is we possibly take the square root of a negative number. So we just need to ask ourselves, is 9 minus 4 cosine squared t, we never want that to be negative, right? So greater than or equal to 0. Is that true or false here? Let's move things over. So I move this over. I divide it through by 4 on both sides. Is this true? Is cosine squared t always less than 9/4? Yes? You could even take the square root on both sides. You get 3/2 less than or equal to cosine t, something like that. Cosine's bounded between -1 and 1, so this isn't. You're never going to have any problems. So our domain here would be what? All real numbers. I'm skeptical. Are you skeptical? I feel skeptical. I did this problem different than I did it in the past, so what I'd like to do is I'd like to open this up, and I'd like to see if I can plot that one. So right in here, I'm going to plot it, all right? Will you all give me a moment? Won't take me long. Oh, shit. Where is it? Okay, it was square root of 9 minus 4 cosine t squared, right? That was the first part. And then cosine t, no, 2 cosine t. Let me delete all this. And I'm going to plot this one in, what do you want? Green. Moment of truth. Although I see something's missing here.
I think the inequality board is off.
The what?
The inequality on the board. Because you have a negative 4 cosine squared t.
Mm-hmm. I moved it over and it became positive,
Oh, no.
and then divided by 4.
I see.
Okay. No, it's all right. It's all right. Let me just try and finish this up here. Okay, that should close that off. That should close that off. Okay. All right, no errors. That's good. Ah, look, there we go. I think I got it. Take them out. Okay, there we go. Do y'all agree that that matched up right on top of the other one? Do y'all see that? I only graphed one of them, though. The other one would be on the other side. Plus or minus. Got it? That's the first time I've ever done that problem that way. I've usually done it the other way, like I showed you over there a second ago, where I restricted on the first cylinder, right, the 3 cosine t sine t. And if you do it that way, the domain restriction's crazy hard. It's. Let me show you what it is. See, what you wind up having to do if you do it this way is you have to restrict this one, which means that, well, I should take a breath here. Do y'all understand what I did doing it this way or not? Yes? You sure? If you go and look at domain restriction here, you have to do 4 minus 9 sine squared t. You need that to be greater than or equal to 0, and when you move that around, that can happen. And then you have to go look at all these different possibilities, and it becomes kind of a pain in the ass. So I kind of like it the way we did it because there wasn't a domain problem. All right, now moving on. Using computers to sketch vector functions is the next topic. And this is just more just so you can see it. All right? Some examples, some cool examples. This is an example of what's called a toroidal spiral. A toroidal spiral. Anybody know what a torus is? A torus? It's a donut, okay? A donut. Oh, a car? Sorry, not. No, a torus. A torus is a donut. So, sacrificial piece of paper. Let's see, anyone have a sacrificial piece of paper? This one. Okay, I got one right here. Imagine if you took this sheet of paper and you connected these two edges together. And this was like really flexible paper. And I take this edge right here and connect it to this edge right here. So I just wrap it around like this. I'd create a donut, wouldn't I? Yes? That's called a torus. And this is a spiral that wraps around the outside of the torus. It's called a toroidal spiral. Got it? Do you see the donut in here? I should have drawn the damn torus in there at the same time. It would have been cool to have it wrapping around it like that, right? That's something I'll do later. But you want to see the vector function for it? Where's the vector function for it? Here it is right here. Highlighted. So the x component is 4 plus sine 20t times cosine t. The y component function is 4 plus sine 2t times sine t. And then the z component is cosine 20t. Now, you wouldn't be expected to like come up with that on your own, but that's what it is. That's what it'll draw it for. All right? That's one example. Here's another example. I'm not going to ask what a trefoil is because someone's going to tell me it's a Girl Scout cookie. Isn't that a Girl Scout cookie? Trefoil? This is a trefoil knot. Okay, so look, this is a curve that draws a knot. So it's very difficult to see it, but this curve knots into itself. I don't know if y'all can tell, but this swings through and goes down on back side, comes back around everything, then back through behind, and then back through. So it's a knot. If you were to pull it taut, it would be a knot. It would make a knot. And I don't have the code for that one, but I can show you what it is. Here it is up here. Again, you don't need to copy this down. This is just to show you that with computers, we have the ability to draw some really cool curves. Let's see if I have any more. That's it. Derivatives. You thought it would never come. So now we want to take the derivative of a vector function. Well, I've got good news. The derivative of a vector function is just the derivative of the component functions. That's all it is. So now, if when you're taking the derivative of one of your component functions, it winds up having product rule or chain rule or something, then you'll have to do that. But you just do them individually. That's what's great. Now, what is the actual meaning of the derivative, though? So in Cal 1, when we had a function, and I say, hey, everyone, calculus 1, you come to some point here, A, and then I say f prime of A. And what is that? Geometrically, what did that represent? You go up here to your function, you find a point, you draw your tangent line, right? This slope of that line is equal to that, right? That's what it was. See, but now we're in 2 or 3 dimensional space, and the question is, what does this derivative represent? So if you have a vector function, the derivative is a new vector function, all right? And for a given value of t, the derivative would represent a vector which is tangent to the curve at the point on the vector curve. So I have a picture for you. I thought I had a picture. Well, you know what? We're going to look at the picture after we do the mechanical part of it. Let's just see how easy it is to take derivative of a vector function first. So find the derivative of this. Well, that's a cool vector function. R of t is the vector function t sine t, t cosine t. Any ideas of what that would look like? If this were just sine and this were just cosine, what do you think it would draw? Should draw a circle again, right? It's going to start at a different place, though. Instead of drawing this two-dimensional, instead of starting here and going like this and drawing circles over and over, it's going to start somewhere else. Where would it start? Again, I'm asking you to ignore this for now. If t was 0, where would you be? If t is 0 right here, where would you be? 0, 1, you'd be here, right? And then if you continue, let's see. Let's plug another value of t that you know. That's a very common one. Pi. So if t is pi, where would you be? Sine of pi is 0. Cosine of pi is Negative 1, so now you're here. But how'd you get there? Did you come this way or this way? So how about pi over 2? If t were pi over 2, where would you be? Sine of pi over 2? Here? And then, so it's actually drawing it like this way. But starting here. Y'all see it? Instead of doing it this way? Okay, but what you need to realize is that this is going to draw a circle. Regardless of, it's going to be a different direction. Do y'all see that or not? Okay, now, but that's not the problem. It's t sine t, t cosine t. How does that affect things? What do y'all think? If this was 2, 2, what would happen? Be a bigger circle, right? If this were 1/2, 1/2, what would it be? Smaller circle. So do you agree that the number out front has always been like the radius of the circle? But now the radius is a variable. And if we start t at 0, what's going to happen? When we start trying to draw this, it's going to be at the origin, isn't it? It's going to start drawing a circle with bigger and bigger radius. So it's going to try and do this, right? But it has to start here. And then it starts trying to draw, and the radius gets bigger and 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 bigger. And so you get a spiral. Do you all see that? Now, I didn't ask you to graph it. I just asked you for the derivative. So let's see. Find the derivative of it. So what's the derivative, everyone? Derivative of that vector function is, what's the derivative of t sine t? Sine t plus t cosine t? Very good. Product rule. What's derivative of t cosine t? Cosine t minus t sine t? Product rule on this one. We good? That's it. That's the derivative of the vector function. So if you know Cal 1 how to take derivatives, you're in business here. You are in business. If you forgot the product rule, then you've got some work to do. All right, find the vector tangent to this curve at the value of t equals pi over 2. Just plug pi over 2 into this, right? R prime of pi over 2 equals, what is sine of pi over 2? 1 plus pi over 2 times what's cosine of pi over 2? 0, so that doesn't matter. Cosine of pi over 2 is 0 minus pi over 2 times sine of pi over 2, which you just told me was 1. So the vector is the vector 1, negative pi over 2. We good? That's the vector. Questions? Sure? Okay. Now I'm going to show you the picture, and then we're going to answer this last part. We have the blue curve, which was us trying to draw the circle with a variable radius, so it's getting bigger and bigger. I don't know why I only went out that far. I should have drawn more. May I erase? Okay. So we went out and when we draw this, I'm just going to press play. The red vector is the derivative vector. So it gives us a vector that is tangent to the blue curve. You all see it? And what we wanted to do was go to pi over 2, which pi divided by 2, right there. And I asked you to find this red vector. And you told me that vector was the vector 1, negative pi over 2, right? So let's just check it. If I were to go out 1, like I'm going to start at the origin. I'm going to go out to the right 1 and down pi over 2. What's pi over 2? So what's 3.14? Do it on your calculator real quick. What's 3.14 divided by 2? 1.6-ish? 1.5. So here's negative 5. So somewhere around here. I think it's about right here. If I draw this vector, that's this right here. Now, if I just slide it over, because I can do that with vectors, right? It's this right here. Okay, so we have found the vector that is tangent to this blue curve. Do you all agree that that looks tangent to you? All right. Already, do you see the advantage of this versus Cal 1? Look at this right here. Right there at the origin, this red vector right here looks like the vector what to you? What vector does that look like to you? J, 0, 1, right? Yes? In Cal 1, could you have done that? What would the slope of that line have been? Undefined. Already we have something more powerful than we did in Cal 1, because we can actually define a slope, a tangent, at a place that we used to not be able to. Right? Okay, so we found this pi over 2. Now let's go back and look at the last thing that was asked. Here's where we were. We were asked at the very end here, find the vector equation of the line that is tangent to this curve at that point, or at that point in time. So now what they want is not just that vector, but they want the vector equation of this line. Well, they want the vector equation of a line. So what do you need for the vector equation of a line? A point and a direction vector. Which do we have? What's that? Is that our point? Is that our direction? Which one is it? That's the direction. That's V. Look, isn't this red vector right here the direction we're pointing? And then the point would actually be corresponding to the vector from the origin to here, wouldn't it? Which would be the vector given to you by taking pi over 2 and plugging it into just the original vector function. And that'll give you the point that you're at. Understand? So we need to get r of pi over 2. So go back and look at the definition of r. r of pi over 2 should be pi over 2 t times, what was it, sine? T sine t, and then t cosine t. This one's gone? No, wait, sorry. This one's gone, right? Because cosine of pi over 2 is 0. And this is what? Pi over 2? So this vector right here is r naught, isn't it? So the vector equation of this line, which I'm not going to call r. Why am I not going to call it r? Because r is already the blue curve, right? I can't call this line r also. So I'll call it s of t. S of t will be this vector r naught plus t times our direction vector, which was 1, negative pi over 2. And then you can put those together, right? I'll do it though. It'll be pi over 2 plus t, and then minus pi over 2t. This is s of t. How y'all feel about this? Somebody gives you a vector curve, vector function. We can now go to any point on that vector function. We can find the vector equation of the line that is tangent to that vector function at any point, so long as we can take the derivative and plug in some values. Good? Okay. We got about 10 more minutes. I don't know how much more I have in notes, so let's just see what's next. Unit tangent vectors. So remember when we were talking about vectors a couple of weeks ago, when we first started talking about vectors, we said if somebody gives you a vector, you can always find a vector that points in the same direction that has unit length. And all you had to do that was to take this vector and divide it by its own length. That's how we found unit vector, pointing in the same direction. Later on, it becomes useful for us to not care about the actual vector itself that's tangent to the curve. That all we look at is what we call the unit tangent vector, which would be a vector that is the same as the tangent vector but length 1. So here I have the picture of the same vector we just had, the red one. The red one, notice how the length of red is changing throughout the entire process here. But if I don't care about the length of it, and all I care about is the direction, then the purple vector, which is this one right here, is always pointed in the same direction. It's just always has length 1. That's called the unit tangent vector. And we just need to know how to calculate it. It's pretty simple. All you have to do is take the derivative, right, which is a vector, and divide it by its own length. So what would capital T of pi over 2 be for this vector function? Notice it's the same vector function we just worked with. So capital T of pi over 2 will be equal to the derivative of the vector function of pi over 2 divided by its own length. I don't remember what it was. Yes, I do. Hold on. It was 1 negative pi over 2. Wasn't that our derivative? That was our derivative of pi over 2? And then I'm going to divide that by the square root of each of the components squared. So 1 plus pi squared over 4. Isn't that the length of this vector? And then if you write it all as one vector, it's 1 over square root of 1 plus pi squared over 4. And then negative pi over 2 square roots of 1 plus pi squared over 4 again. So I just took each of these components and divided by this number, and that's your unit tangent vector right there. Like I said, later on it'll become useful. Because what we'll do later is we'll be interested in a different vector that we haven't even talked about yet. This is like when we deal with what's called flux. So we'll have some sort of what we call a vector field. You can think of it as like gravity. Like we're sitting here in three-dimensional space and we've got this force pulling on us. That's a vector. And then we're trying to move in a direction, but we got this force pulling on us. And to get our heads around all that stuff, what we'll do is instead of looking at the vectors, we'll look at the projections of vectors onto tangent vectors. It's just a little easier for us later to work with it. So just want to make sure we know how to compute it. Any questions? We're good? This is an example of a three-dimensional one. See how much more I have in these notes. Man, geez. Okay, I'm going to leave this for you. Okay, I'm going to leave this one for you to do on your own. It says for you to find the vector equation of the tangent line to this three-dimensional curve, but there's something missing in here that I haven't given you. It's very important. Like I give you the vector function, right? I want you to find the vector equation of the line that's tangent at this point. So there's some curve sitting out here. You know, it's doing something, and then at some point, that point 0, 1, pi over 2, you're supposed to tell me what the vector equation of the line is that's running tangent to that. In the previous problem, what was it that I gave you that allowed us to figure out all those answers? Well, we took the derivative. That was the vector function. We had that, but there was something else. I gave you t was pi over 2, right?
Yeah.
I gave you the time. This isn't giving you the time, it's giving you the point, right? If I give you a point on a vector curve, can you tell me what point in time it happened? You would have to resolve that t, wouldn't you? Can anyone tell me by looking at this what the t would be in this problem? Pi over 2. How'd you get that? Because z is t is pi over 2 is obvious right there, right? Also, sine of pi over 2 is what? 1, and then cosine of pi over 2 is 0. So whatever your t is, it has to satisfy all these three at the same time. But this one is like given to you. It's a gimme. You see that? So you have to get what t is, and then you can go figure out all the other information, right? All right. I'm going to leave that to you. Second derivatives. Boy, we're moving through Cal 1 fast, aren't we? First derivative, second derivative. So do you remember what the second derivative was in Cal 1? Inflection points. Remember that had something to do with that? Right. Acceleration had to do something to do with acceleration? All right. Well, all we're going to talk about right now is that the second derivative is just the derivative of the first derivative, right? Okay. Now, what is a smooth vector function? Now, there is not something like this in Cal 1. This is where vector functions are going to separate themselves a little bit from what we saw in Cal 1. A smooth vector function. A vector function r of t given on some interval I is called smooth. If the derivative is continuous, that means it exists on I, and the first derivative is not zero, except possibly at the endpoints. What? So look, going back to Cal 1, would you consider this to be, if I took a parabola and let's say this is 2 and this is 10, and let's cut this parabola off, would you say in Cal 1 that's a smooth function?
Yes.
In Cal 1, yes? You'd say that's smooth, right? But notice right here, at some point in here, that the derivative is 0, right? In vector functions, if your derivative is 0, it's not smooth. You can't have a 0 derivative. Do y'all see what I'm saying or not? In order to be smooth, your derivative must be continuous and your derivative can't be 0. So in Cal 1, this wouldn't have worked. We wouldn't consider that smooth in this class. So let me give you an example. Smooth functions. Is this function smooth on the entire number line for every t? So first we're going to do this. We're going to take the derivative. We're going to ask ourselves if the derivative is continuous. So what is the derivative of cosine squared t? Negative 2 cosine t sine t. I can simplify that even more. 4t cubed, right? That's it. That's the derivative. Go back here. I just noticed this typo here. This is supposed to be the 0 vector. The derivative cannot be the 0 vector. Pardon. So is this right here continuous? So is r prime of t continuous? Well, is it defined on all the values of t that we're trying to plug in? If you try and plug in t's here, are you ever going to have any problems? No? How about t's in here? Any problems? No. So, yeah, it's continuous, sure. But now what we need to check is this. Is r prime of t not equal to 0, except at the endpoints. Well, do I have endpoints? Is t on an interval? No, so I don't even need to consider this. I basically need to make sure that that derivative is never 0. Is that derivative ever the zero vector, damn it? Is that right here ever the 0 vector? Is there a value of t that I could plug in that would spit out the 0 vector? How about 0? What's r prime of 0? You get, well, sine of 0 is 0, right? So that's killed off. And then here you get 0, and that's the 0 vector, isn't it? Yeah, there's a point in there where you have a 0, right? So it's not smooth. It's not. Let's look at the graph, and I think you'll see why. There's the graph. Oh. Okay, let me slow it down a little bit. All right, so time, look at t equals 0. Here's negative. Here we're getting closer to 0, right? About there. Well, something really crazy just happened. You can see it in the picture, can't you? It's like a cusp. But look at your tangent vector. It's going like this, and all of a sudden, boom, it's flipped the other way. Do you see that? So your tangent vector goes from something pointing in this direction, and instantaneously, right from there, it's like this. In Cal 1, it was this issue when we had a cusp. We would say the derivative didn't exist there in Cal 1 because we'd have a positive tangent line, and all of a sudden, bah, it'd flip. We also had this happen on corners, didn't we? This is what it's like for us in vector functions. We get something like this. And that happens when our derivative is 0. Kind of interesting. Vector function. The derivative of the vector function is 0. 0 vector. Thank you. Keep saying that. All right. Oh, I'm out of time. Boy, we were supposed to start 10:08 today. It's okay. Hey, a quick thing on the take-home tests. All right. First thing it says here, due at the beginning of class. That means when class starts, this is due. If you don't turn this in when it's due, if you come in late to class, then you need to have sent me an email, texted me, something. I'm running late. Here's the reason why. You're in the lab. You're getting help. You take an extra 15 minutes to get a problem done that someone else didn't do. That's not fair. Now, I'm not saying that's what you would be doing, but I think it's fair if we have a deadline, everyone's got to turn in at the same time. Because I've had students before, they just don't come to class because they would rather go to do the test, and at the end of class, they come in. I will not accept that. So there will be penalties if you turn it in late. Understood? Yes? Okay. If you did not turn in the test, make sure that you talk to me. Stay after class. Let me turn off my recorder. You can start your homework from 10:07. I don't think you can do it all, but you can start it.